set. We got it all hot and ready to go. Whoever's dissing Linux for not having graphical capabilities can... Anyway, it'd be nice. All right, I'm Carson. Thank you for coming. If you're here and if you don't understand what AST is, don't worry. I'm not even going to actually define the acronym until like almost through the end of the talk. Like, you don't need to spell it. You don't need to understand it. We're going to get a ton of value. It's going to be a lot of fun. We're going to deal with fun shapes and bright colors the entire time, and it's going to be a blast. I work here at Weave, work on the developer experience team. I call myself the DevX-O, the executive officer. I kind of make it so. And I want to just quickly mention Z Manzilla, who I have commissioned for the art. I have a personal pledge to pay human artists to make human art that I will put in my slides, and I will only use human-made art in my slides. So you can commission them. Go ahead and find them at their website. I'll have that link at the end as well. Really affordable and fantastic artist. Speaking of, there it is. You'll see this and variations of this that I made throughout the talk. Why? Right? I like to talk with the why. Why even learn about ASTs? Again, I won't even define it yet. I'm not going to start with the AST diagram slide that every other talk or web post will start with. I wanted to talk about, like, why would I want to learn this tool? And the short answer is value. I'm going to kind of stretch this tree metaphor a whole lot, so stay with me. Right? You learn how to chop this tree down, and with the wood, the lumber that you get off that tree, you can build amazing things. It's this very simple idea that once you learn it, it's the foundation of enabling all these things you didn't think were possible before. So I'll work through this, and we'll show you some of these examples towards the end here. Let's make sure this is up and working. Okay, so do not tune out. No, we're getting to the end of the conference. Everyone's tired. Everyone wants to just go to the after party. Come find me at the after party. We'll drink together. Some kind of general idea of what we're going to go through. I will not start with the what is the AST slide. We're going to dive straight into not understanding ASTs at all and just do stuff with it, right? That's how I got there. That's how most of us start. We're like, I don't know what it's doing. I just need to get some stuff done. And Carson said this is how. Then we're going to go into fun shapes, bright colors for almost the entire middle of the talk. Because what I learned when I went to do an AST talk in Go is the AST package in Go is not interesting. It's not the hard part. The hard part is the data structure. The hard part is just understanding ASTs in general. And I have come up with a way to do that using a toy you might all recognize. And if you master that toy, you can master ASTs. Then we will dive back, once we learn our shapes and colors, we'll dive back into the actual Go AST package. And at the end, I'll do a bunch of bonus rounds where we cover, like, okay, now we understand this. What does this really mean in deeper depth now that I really understand it? Whew. Okay. So first thing, want to get value. I'm going to go straight into really boring code. And I want to actually point out that there's more to your code than the thing you build from it. There is the code itself. There's all these ideas and these decisions and information encoded into your code. And wouldn't it be really nice if you could get all of that stuff out in a meaningful way? In this case, I want to get all the comments out of this code. This is meaningful data. People don't put comments in their code because they don't think it's read. What if we took all those comments out, including the things they're attached to, and auto-generated documentation? Now, there are tools to do this that are better than what I'm going to write, but I'm going to use it as an example, right? So let's do that. I could just grep, right? I could just find and replace, like find all the slashes, but that's not going to be accurate with multi-line. It's going to find slashes that aren't related to comments. I want to be code level accurate about the comments and where they're coming from. So, like I said, cut the tree down. I don't even want to be nuanced. We're going to chainsaw this tree down and get our value right away first. And batteries included, standard lib. All you have to do this in Go is import these 3 packages. I will not define them. You don't need to. Again, someone just told me this is how I do this. I'm not going to learn it. I'm just going to, we'll get there. But we're starting out with, I just want to get stuff done, right? So we import AST, parser, and token packages. And we write a little bit of code, right? The first bit of the code goes in and just gets the argument of the file we're going to parse, loads the file. It creates this thing called the token file set, which, again, I'm not going to care about right now. You don't have to worry about it. Something we have to build. Then we take the parser package. We give it our file set, our file name and content. And in this very special option that says, don't just throw those comments away, keep them around because I need them. And then we get this AST file back, which is just a data structure. We'll dive into that later, but for now we're getting value first. So the core of what we're going to do to get all those comments out is just this small AST inspect function. So we will loop through. We're going to call AST inspect. We'll give it our file and a function that it's going to call on every bit of code. Again, I'm being very vague. We will come back to this. For now, just understand this function is going to take every little chunk of my code. It's going to get passed to my function. I will then look and see, is this some sort of declaration, a variable, a constant, a type, or is it some sort of function declaration? Those are the only two things I care about in this code base. I'm going to throw everything else away. If it's either of those things, I'm going to print out the information about them from what's given to me, and then I'm going to return true, meaning keep looking for more of them, right? Don't stop. You don't have to understand this. I just want to go straight to value. So let's actually do it. Let's take that code from before and pull it over here and run it. And to nobody's surprise, it works, right? Like, this is great. This is code level accurate. It told me exactly where my declarations were. It told me what type of thing they were, and we could get more data out, but I'm keeping it really simple in this example. And no matter how crazy my code gets, this will always find all the comments for the things that I'm looking for. All right, so here's some really deeply nested code. Again, I've got comments all over the place. I'm only specifically looking for type declarations, variables, constants, functions in the code that I've written. I could get anything, but we'll just start simple. If I hit run here, then yeah, no matter how weird and deep and complex my code is, it will find all those comments and say, here are the comments that were attached. And I wrote something like impossibly silly just to show, like, this is crazy code. Don't even try to understand this, but like, there are some types being declared ridiculously deep in my code. And without me changing anything about the code that I wrote to find the comments, I can run it and I can get all of this information, right? Again, there are tools that do this for you. You do not need to write this. There's GoMarkDoc, which just does this, but it's a neat example. So what is a more practical use case? Again, straight to value before I dive into the how this works. So, practical use case. Unfortunately, we all have run across this in code that does something that doesn't make sense, right? And it does it for reasons. Somebody's bad ideas are sticking around forever and going to bite us in the ass forever. And this is the case in this add. It takes A and B, and it always adds A and B, and then one more. And we don't know why, but it's really important, and I don't want somebody to come in here and think that's a bug and take it out and break prod, because that +1 is important for reasons that I can't control. So how do we document this, right? We document this in our documentation, and that might be in some file a million miles away from the code where I won't stop somebody from breaking this if they're looking at it during, they're changing this code. So at Weave, we decided, actually, you know what? Let's put, we wanted these architectural decision records, ADRs. Let's put those decisions in comments next to the code that is implementing those decisions. Let's put them as close as possible. The silly things we have to do, maybe they're even important things or good ideas, and we want to say, this is why we're doing it this way, and we want to put it next to the thing that's doing that. But of course, putting it here makes it hard to find and to see an overview of all those silly decisions that a code base has made. So we wanted to go ahead and take all of that and extract that out into a dedicated document. So here's some code to do that. Again, iterating a little bit on the code you saw before. We're still reading the file, giving it a new file set, parsing it. We're not going to loop over it in this case. We're actually, because if we go back, this is kind of a free-floating comment. It's not actually attached to anything you'll notice. It's not above a function or a type. So instead of doing that, we also get this just big slice of comments that are in the file, and we can just range over those, find where they're at. We use that file set to kind of locate metadata about what we're looking at. We're going to see, hey, does this start with a string ADR? And if it does, we'll print out a bunch of information about it, the file it came from, the position, and the actual comment. So really, really simple stuff. And this is more or less how I came to ASTs in general. I needed to get this, and someone told me AST is how you do that. I didn't know how AST worked. I just wrote this code. And if we run it, you'll see, here you go. So we wrote this, you redirect that to a file, you do it in your CI/CD pipeline, and you have auto documentation from your decisions from your code surfaced all the way up in your markdown just at the top of your repo. And we do this, and this is like the first thing I did at AST. It's been massively helpful to get that documentation, again, surfaced up, but sourced next to the place that's actually making the decisions. So that's where I stopped for a long time. I didn't even learn ASTs. I just used the AST package to get this value, implement the feature I wanted, and I moved on. But it got this AST thing in my head, and I couldn't get it out after that, and it just kept kind of eating at me. So again, now we get into the fun shapes, bright colors portion of the talk, where I'm going to leave Go behind. We're going to go into something else. Hopefully you've all recognized this complex puzzle device, right? And we all feel like, does anyone here feel like they've not mastered this puzzle? Okay, you might have a little trouble, but anyone else that feels like they can understand this and solve it, can understand ASTs, because ASTs are shapes, and they're just a shape puzzle. And I'm going to do a lot of the talk now just doing that. So here are the shapes we're going to work with, right? And you might start to recognize them here. We're going to come back to this. I've got more toys. So we've got a triangle. A triangle can contain 0 to 1 circle inside of it. We've got a subtype of triangle. I made it extra complicated. I could have used a different shape, but I wanted to do a subtype for kind of analogous reasons to the Go types. So a triangle can contain up to 1 circle, or it can have a character inside of it. We can have a circle with up to 2 squares and a square with up to 3 triangles, right? And you can see that there's a loop here, because then that square can have triangles, that can have circles, it can have squares, and you can build a very, very complex shape with shapes and shapes and shapes inside of it using just these 3 or shapes, or 4 if you count the triangles separately. So let's start with the easy mode of this very, very complex puzzle system. We've got a square with 2 triangles in it. They happen to be character triangles that say hi, right? Super simple. It may not be a surprise to you that I can represent that this same way. I can say there's a square with 2 children, 2 triangles inside of it. These are, and I have a clicker, these are the same thing, right? One is just a representation of the other in what we'd call a graph diagram. And we're starting to see a very specific shape that I have not named that's part of the AST acronym, right? So everyone hopefully is grokking that these are the same thing. So let's go a little bit more complex. Here is a circle with some triangles, with some squares and some triangles inside. Getting more complex, getting more deeply nested. We're starting to see something like this up here. Again, we can represent all of these the same way. These are the same thing, right? In one side on the left, we've got the actual physical nesting of things inside of each other, and the one on the right, we've got a diagram just with parents and their descendants, right? And you'll start to notice some important things about these kinds of diagrams is that they kind of always go in one direction. Doesn't have to be down, but down's pretty traditional. And they never really loop, right? There's no way to put a circle inside of itself physically in these puzzle systems. Like you can't literally, just like if you can come up and draw that for me, come do it. But I don't think I can actually have a circle that has a circle inside, the same thing inside itself. So we'll go a little bit harder. We're gonna make this the most complex one. We've got a circle with some squares, with some triangles, and one of those triangles happens to have another circle with squares and triangles. You can't even read it. It gets really small really quickly. If you'll see this, it gets really, really tiny, and that was the biggest I could print that base on my printer. But the diagram's actually pretty easy to read, right? It's still pretty simple. These are the same thing, and you are starting to see the T part of AST, which is tree, right? Tree meaning branches. It doesn't look quite like a tree, but if you imagine you got the root of the tree, and you got branches, and those branches have sub-branches, and those branches have sub-branches, and you can always kind of trace them back to their root or down to the children. Again, trees never grow. I'm sure they grow back into themselves technically, but stay with me. It's all unidirectional, right? This is graph theory, but it's acyclic. It always has to go one way. So everyone feeling pretty good. They understand these shapes so far. Okay, so let's go back to that inspect code from before. Remember I said you didn't need to understand what the thing was? Let's pretend instead of node here, we've written our inspect function, and node is shape, right? We're saying, okay, call this on every shape in this tree. I'm gonna give you the circle at the top, and then just tell me, okay, give me the first shape. And I get to, instead of looking for a general declaration or function declaration, I get to look for, is this a square? Is this a triangle? If not, go to the next thing. Go to the children of that. Is that a square or a triangle? And I can just keep looking down and down and down. I'm only looking at one piece at a time. Something else is doing the work to kind of figure out what the different types of children at each phase is. But I don't have to know that. I'm just looking for data shapes, right? That's all that was happening before. The shapes just happen to be Go code text shapes, but they're just shapes. So let's go back to text, right? We're moving away from the raw shapes back into text, and we're gonna do that with a text markup and Go structs. So our triangle, all of our shapes are going to implement an interface that just has a depth. This isn't technically enough to accurately represent all these things, but it's enough to get the idea, right? How many layers down do you have? In other words, how many parents do you have? Do you have 0 parents, 1 parent, 2 parents? So any shape, all these shapes will have some position that they're at in that depth. Our squares can be represented with go figure square brackets when we see them in text. And struct-wise, they're just gonna implement the shape interface. They're gonna have a depth, and they're gonna have up to 3 triangles, right? So that's an array where it can have 0 to 3 triangles inside of them. Triangles are a pointer. We'll get to that in a second. But really basic struct for squares. Circles, the same thing. They are a shape, and they happen to have up to 2 pointers to squares inside. We may have none, may have 2. Triangles are going to be a subtype. Again, we're using some interfaces here to kind of add a little complexity because this is more realistic to when you're doing real AST things. All triangles are shapes, but we're going to use this little marker method to have the compiler warn us if we try to jam any old shape into a triangle. It has to be a shape that specifically says, no, I promise you I'm a subtype of this triangle shape, right? So there's a lot of ways to do this. The GoAST package doesn't use marker methods. It's just a simple way that I'm doing it for our samples. And again, another subtype of triangle circle where inside of it has a depth that has up to 1 circle inside of it, and then it is a triangle, it is a shape. So we're all good. We've got square brackets. I'll actually come to the summary here. Let me go to the character. So one more triangle. It's going to have quotes, and again, a depth. It is a triangle, it is a shape. Here's the summary of that. Square brackets for squares, parentheses for circles, angle brackets for triangles that happen to have circles inside of them, and quotes for triangles that just have a character. Right? It's just the shapes. I'm just having to represent them instead of with actual physical shapes. We're going to represent them with characters, and things inside are just between the markers, right? Things inside a square are just between the 2 square brackets. So let's go back to our examples and convert them to text. So here's that very first example. These are all equivalent, roughly, data ideas, right? It's a square with 2 triangles inside it. Each of the triangles has 1 character. All 3 of these things are the same thing. And we can kind of understand there's a square with 2 triangles inside of it. Not that complex. Again, these are really great to represent because there's no cyclicalness in any of these. These all can't just have magic loops because text has to contain a finite number of things. Here's the medium shape. So again, same idea. We've got all of the shapes, we've got the nesting, and here's the text representation. And you're starting to see patterns and subshapes, even in the text, right? You can kind of really at a glance with some of these see that you've got circles with squares inside, just looking at the text. And we're just making this up as we go, but we've written our own kind of abstract syntax tree shapes, structs, and markup that can be extracted out. And here's the most complex one. Again, that's a really complex data, but especially in the text representation, it's a little bit easier to read. And this is the one I love to look at because I think it really shows like, this looks incredibly complex with all of these symbols, but it can break down into the thing on the right, right? The text here can still break down into that subtree on the right. It's just shapes inside shapes inside shapes. So we're going to go all the way back into code examples. So our examples for code, again, we've got our square with 2 triangles inside of it. Here's the text at the top where we've got the brackets, and here's our struct representation of this. I'm really walking you slowly back into this because when we dive into the Go stuff, it's going to be this, but with a lot more data. But hopefully this doesn't surprise anybody that this thing here is, our struct is the same thing as the data. We can take that diagram or the tree diagram or the text here and convert them all and represent them pretty accurately with this struct here, right? Where we've just got a square at a depth 0, it's got triangles, and the triangles happen to have characters. So really, really kind of simple. Don't worry, it's going to get a lot more complex pretty quick. Here's this middle example. Again, going back to the text at the top and the struct representation. And again, you're starting to see kind of patterns emerge. You're starting to see that squares kind of look a certain way. They always have repeating patterns. You can kind of just even eye them here. The shapes repeat themselves. It's just data containing data, as deep as you need to go. And you could, again, do really complex versions of these. And we'll actually go to the most complex and you'll start to see that. So here's that same diagram from before with all the shapes. And here is the text diagram, and it gets really big. And this is where really the repeating patterns start to see, right? So if you look at the text here, the top square and the bottom square in the text are really identical. They're almost identical, except for the top one has 2 characters in each chunk instead of 1, right? So our representation in GoStruct is really simple. Here is the first square. Here's the second square. They are almost the same thing, right? These are repeating patterns. And I'm going to come back to this. Like it's a lot of nesting. It's deeply nesting. You'll see stuff like this a lot when we work with the GoAST package, but don't be scared. It's just shapes and shapes. You can always kind of take a piece of it out in isolation and look at it. If you cut that tree off, if I go all the way back, if you cut this tree off at like one of these bottom circles, you can still analyze it entirely without knowing its parentage, right? So you can always rip pieces out and analyze them in isolation if the thing is too big on its own. So we've taken our axe to all of our trees. We've dealt with bright colors, fun shapes. We're starting to understand this idea of how you can take a lot of things, right? That was shapes, and represent them with an abstract syntax tree, which is, in case you didn't know, that's what the AST stands for. So let's take this back into Go code and get some value out of it. But before I do that, I have to go to some more toys. I have been crafty lately in my talks. I'm going to put this down, and I need the tape. So 1 second.
You just went through all your slides.
No! Just put something down, and it really went. Wait. Aww. Oh, yeah. So, I couldn't help it. Wow. There we go. No, that's good enough. I see the one. So, in case I got my visual learners with me and you wanted to go even further and take that kind of physical toy idea from what I was showing you before, I designed and printed, and in the link we'll have at the end all my contents out there. I have the models and everything. You can go print all of these. If you have they have a pretty high tolerance, so you have to have a decently good printer to like have the snaps snap in to connect the arrows. But it gives you, again, that's kind of a really fun physical way where you can walk down and say, well, I'm looking for function calls, and my function calls happen to be triangles with circles inside them, right? So you start at the top and you say, here's that. Is that a triangle circle? No. I'm going to look down to the first child. Is that a triangle circle? No. Next child. Is that? No. So I'm going to go to the sibling of that one, and then, yep, there's my function call. I found it. I can print information attached to it, like its parent, or I could follow it down to see maybe these represent the arguments being passed to that function. Again, that's all that inspect function that's doing. That's what most of your ASTs are doing, is just representing things that have things that have things that have things inside of them. I have got a bunch of things to give away, not exactly right now, but come find me. I have made this little abstract syntax toy, like carry case, that has some snaps and shapes. I don't know how I'm going to give this away. I'm just looking for somebody that is as nerdy as I am and cares enough to want it. I have extra shapes. Come find me. I couldn't help but print toys and get a little physical just because it's been fun. So, okay. I actually even have a little Go mini one if somebody wants to come find me afterward as well. Toys are done. We're going to go out of the realm of colors and shapes and start to bring this back into real Go stuff. So back to the AST package. We know that these are all the same. I've already described that this is all the same representation. I'm cutting it off at the bottom. And again, I want to really drive home that what the inspect function was doing is just walking down this tree. And in our case, that tree isn't this physical tree anymore, but it's actually just looking at children. So that inspect function, you just need to write some very light code that knows how to look at circles and know that circles have squares, and just call each of those shapes with the abstraction of that interface, right? Passing it back as an interface, which is why you have to typecast, because you have to eventually say, well, they're all shapes, but I'm looking for this shape. And is it that? Okay. So if you can understand this, we're going to move on into the Go stuff where it gets a lot more complex with the data structures, but the ideas are all exactly the same. Okay, so let's do some type examples of Go AST. Again, I'm not going to spend a ton of time diving into this for you because knowing these, this is just looking at reference docs now. Like, now that you understand ASTs conceptually, you can apply it to Go's AST package, you can apply it to AST packages from all sorts of sources, and I'll kind of get to that as we get to the end of the slides. But here's some fundamentals, the ones we've been working with, right? So gendecal, remember we were looking at that in our previous, or I don't know how you say that, gendecal. This is just a shape, right? This isn't that much more complex than our triangles and our squares and our circles. They're tracking more than just depth now. They've got things like position, which is like line number and column number where things were. Or they're tracking comments that were attached to it. Remember, we were getting those comments from before. They're tracking nested things. So general declarations can have nested specs inside of them. That's all that we were looking for before. And we can get any of this out in that inspect function, right? We have access to all this data. It's there. We just were only looking for pieces of it. Functions, again, we were looking for those before in the inspect. Same thing, some really basic stuff. Functions happen to have field lists, and they have bodies, and they have types, and they have all this stuff. But again, we're just looking for a specific shape that is the shape of our function. We've got things like selectors, which if you didn't know, that's when you do a something dot something. These are specifically fun. I like to point these out because selectors, the X is another nested expression, which can be any kind of expression. So selectors, you kind of imagine this is important if you have something dot something dot something dot something. That's a selector with a selector with a selector with a selector inside. It's just a chain of selector shapes where it's a new shape containing another selector shape. I could have easily had a square with a smaller square inside of it. That's all a selector is one of those is just the same shape again. We have idents, which aren't too bad. They're, again, they're kind of like the constants of your code that aren't the quoted things. So if you look at log and print line, those are identifiers in your code calling out specific things, in this case, a package and the function in that package. And they've got things like, again, their name and their position. We got function calls. I don't need to, I'm not going to go into detail. You can go look at the AST docs on this. But again, function calls have the function, which is some kind of expression. So that expression might be a selector. Or they have args, which just is a slice of expressions. Again, just shapes inside shapes. And sometimes they're very specific subshapes, and sometimes they're very generic subshapes like this. So let's do one more practical example before I bring it home. Practical example here is we're talking about the slog package, right? And in order to migrate to slog, I have to know where I'm using the old log package to update it. Ideally, I'd love to rewrite this, and we'll talk about that in a second. But let's start with just, I want to find, in this kind of deeply nested complex code, all the times where I use one of the old log functions from the old log package, print those out so I can fix them. Again, another tool you don't need to write. There are tools that do this, but easy idea. This is the same code from the first two examples, right? We've not changed any of this. We're using the AST, the parser, the token package. We're loading up the AST file. And we're going to use inspect again. Stay with me. This is normal. This might seem, your instinct as a Go developer is like, that's so deeply nested. I hate it. I should flatten it. Don't flatten it. Like, this is canonically fine, normal dealing with an AST. It gets way worse if you try to flatten it. I promise you it's okay. But if you squint, or maybe squinting's hard, but what we're looking at here is this first thing is a call expression, a square. Next thing is a function, a triangle. The next thing is an ident, a circle, with the first thing inside of it being one thing and the second thing inside of it being another, right? This is just very complex code to say I'm looking for a square with a triangle with a circle inside of it. And that I know is a specific call to log.println, log.printf, or print, right? And then that's pretty much all AST working with is doing is somehow dealing with traversing this graph, looking for shapes with inside shapes to find the kind of code. If you remember the nil pointer dereference stuff, right, that amazing talk, you know what they used to do all of that analysis? Like this is it. You learn this tool. That's what all of that stuff is built on, is this kind of thing. And there's actually even more use cases beyond just Go analysis. But if I run this code on the thing from before, I very quickly, with minimal, that was like almost no code, right? I can run this across my file. And by the way, this AST is super fast. You can call AST. There are ways to do it across an entire directory, not one file at a time, on your whole code base, and it's like sub-second. Like you can run it constantly, all the time. It's impossibly fast to do this analysis. We do it every single time we generate documentation across entire giant code bases, and it's almost instant. So this is where I can go back and fix all those and run this command until I see no more outputs. How did I get those shapes though, right? Let me hop back one more. How did I get, oh, I'm just hiding it. How did I get like this specific series of shapes? It's like, how do I even know that that's what I'm looking for? And there's a couple ways to do that. The one I actually highly, highly recommend is astexplorer.net. It's a really, really great website where you can go to astexplorer.net. I'll actually pull it up now. Try not to go through all my slides this time. Right? And this is the Go code from 4, and it's great because if you click in on any part of this, it auto drops in. On the right is the big, giant, hugely deeply nested structs within structs within structs that is this code base on the left. And I can go in and click on and highlight over specific things to say, yeah, oh yeah, I'm looking for a selector with an ident inside of it, and that would be my printf. Or if I highlight this, I'm looking for a call expression. Like you can take this, you can extract bits of it out, and you can use this to figure out, put the code in and figure out what you're looking for. And it's way easier. If you don't have these tools, I use sanity.io to like pretty print entire structs. And the structs are like really great pretty printed, just looks like giant JSON. And you just find the shapes you're looking for and code them up. So the other thing I'll point out, again, I talked about value. look at how many languages have ASTs. You can represent a ton of things with ASTs. Not everything. We were talking about certain scripting languages and things just are not static enough that can even have really an AST or an effective one. But there's tons of stuff in here. And we used ASTs from other languages to some great effect. And I'm going to get to that before I run out of time.
Of time.
No, that says 4:28.
Okay, you've got 2 minutes.
Okay, I got 2 minutes. I need 2 minutes. Don't take my 2 minutes. All right, next thing is AST package from Go is amazing. It's not great for rewriting. You can load it, you can slightly tweak it, and you can definitely write it back out. GoFump just loads and writes. But if you want to really change it, like find all your calls and rewrite them or move function calls around, use the DST package, unrelated to Go, but it interops with the AST package, supports auto imports updates, it tracks like the source path of package imports where things came from, and does rewrites better. So just know DST exists. If you're going to do some automated rewrites, just know about that. It'll save you time. Finally, some practical use cases. Filter strings. We recently implemented, are working on implementing standardized filtering across the Weave APIs, where we take these AIP-compatible filter strings, parse them into struct fields or SQL statements, and there's a library that can just turn these into an AST. And as soon as I saw the AST, I was suddenly instantly empowered, because now I know how to find out all of the information about that filter string in a really sound and understandable way. Something really amazing we've been working on is a VS Code notebook extension, where you define API calls to the Weave API surface, the internal API surface, as a developer here at Weave, and you hit play and it executes it and shows you the results. And it saves us all as markdown files. I could go on for an entire hour on this. But we wanted to hover over like namespace ID and tell the person the comments from the protobuf that defined that field. And so I need to find out if you're in a code block, what code block, and if you're in JSON code block, what path you're hovering over. There is a markdown AST where you can find out if I have a position, if I hover over a position on this file, I can find out using that AST in the position I'm hovering over, what block I'm in. Then I can sub-parse that with a JSON AST to find out what package path I'm in. And it actually enabled this feature where inside this notebook, inside JSON, inside Markdown, you could hover over a field and we could figure out where you were because we understood ASTs existed and can give you the documentation from the API for this call, which is really, really cool. I didn't think it was possible. I thought it was a pipe dream. That is it. I'm out of time. Hopefully you're starting to see the value. Again, this is a tool. You may not use it, but you'll go and start to see these patterns and these shapes within shapes. And hopefully you get just a bunch of value out of it. Again, even outside Go, this is something you'll see in a lot of languages. Go's just an amazing language because it's so accessible to look into the internal types, and these are shipped with the language. Thank you.